Okay, absolute conditional convergence as well as divergence. I'm looking at problems 12 through 14 on the practice test. First of all, I want to make sure you're clear that if you take the absolute value of the terms and then determine if that different series converges, you have absolute convergence on the original A sub n series. Done. However, if you don't take the absolute value and you get diverge, as you see at the bottom, then it's diverge. You don't need to do anything else. Only conditionally converge requires you to test two entirely different sigmas. So the infinite series with A sub n, if you find that to converge, but the absolute value of the terms within series, the infinite series, diverges, that's when you have conditional convergence. And let me help you to understand the difference. If I have an alternating series and I go negative, positive with my terms, then basically say this is the quantity of my first term and it's positive. Now, if I then add a negative number to it, then I go all the way back and my sum is now just this tiny bit over here. Then I add after that. So I add this much, and that takes me over to here. Then I subtract, and all of a sudden the sum goes down again, and now it's this much. And it just keeps going up and down and up and down. Now, if, let me back those up, if I absolute valued all the terms, then I would be taking these negative vectors basically, and I would be turning them to all go in the positive direction. So I'm going to make all these that are going in the positive direction, or sorry, in the negative direction, head in the positive direction. Now, if I look at the sum after I've absolute valued the terms, I'm going to have to zoom out a little bit here. Looking at the sum of all of these terms, now that I've changed the negative to positive, got to zoom out some more. Just these first 6 terms are taking me from 0 out to wherever this length is. However, when I was dealing with an alternating series, the sum of those 6 terms was only this distance. So compare those distances and then think about an infinite number of these. So you want to see that when you add and then subtract, and then add and then subtract, you have a much better chance at being able to have an infinite quantity of terms converge to one particular sum. However, if you absolute value all of those terms that were making it go back and forth with its partial sum, now it's just creating a longer and longer length all the way out. And it has a much greater ability to do diverge. So with that said, I want to go back to this picture again. If I absolute value the terms, that was taking all those ones going in the negative direction, flipping them around, and then just letting them add and go further to the right. If that is able to converge with those terms, then you say that the series of A sub n by itself, just let me write that down. So your given series with A sub n, that absolutely converges. If you can absolute value its terms and it still converges, it's absolutely convergent. However, you might run into the situation where the series just completely diverges. In that case, if you absolute value the terms and you get diverge, you could be in a conditionally convergent situation. And then you have to go through another test and check if the original series converges or diverges. So what I'm saying is, if you realize you're going to need to show diverge, entirely diverge, don't do the absolute value and check to see if that converges, diverges. All you have to do is take the series as it began, show through some tests that it diverges, you're done. If you need to show absolute convergence, and you start by just testing the series as is, and you get converge, you might have absolute convergence and you might have conditional convergence. So if you get converge for just the way that it is, you have to go and test the absolute value of all the terms in a separate sigma with an entirely new test. And if you test it and you get diverge, then both of them had to be done. But if you test it with the absolute values and you wind up getting converge, you wasted time bothering with testing whether you have converge or diverge with the original series. So you want to take the time to figure out, what situation do I appear to be dealing with, before you go wasting time testing two series when you only needed to test one. Now, in tomorrow's test, you're going to see these problems given as alternating series. So I am promising you that you are going to see an alternating series. And I will only give you, oh, I take that back. Hold on. Let me write this out. You're going to have a negative 1 to the n, or a negative 1 to the n plus 1, or a negative 1 to the n minus 1. You'll have one of those, and then the rest of it is a formula. And you want to look at what the rest of it is. So let's take a quick peek at 12, 13, and 14. If you take out the negative 1 to the n plus 1, you are left with 1 over the cube root of n. Number 13, if you take out the negative 1 to the n, you are left with the square root of n divided by the natural log of n. Move on to number 14. If you take out the negative 1 to the n, you are left with 1 over n cubed. Now let's take a look at just those terms. Those are looking at the absolute value of the formula in a series. So I've got 3 of them. I'm going to list them over here. And you want to think about what is happening with each of these as n approaches infinity. You should see pretty quickly that these two, if n is approaching infinity, then those are approaching 0. Then as long as you additionally have that you know that that is a decreasing series, Both of those are going to pass the alternating series test. But before you go and write down a bunch of work, do you need to show that for both of them to finish those problems up? What you want to do is, first of all, realize that when I give you an alternating series, you're dealing with an alternating series that's either going to have, it can be compared to a geometric series or a P series, or you can throw in a ratio test with it if it's got a combination of things. These two are P series when you take the absolute value. Take a moment to think, is it a converging P series or a diverging P series? This one is a converging P series. So realize that if this is the absolute value of the formula for the original series, and I can show that that converges, I do not want to waste my time with the alternating series test. I want to just go straight to, given this formula, wait a minute, that isn't the one, ha ha ha, number 14. Given the formula, I am going to test the absolute value as a series, which is equal to the series 1 over n cubed. Then you can say that this is a P series. It converges because your P is 3, 3 is greater than 1, and in a P series, that's a converge. And because you showed that absolute valuing the terms gave you a converge, you have absolutely converge. And the only test you needed to use was P series. Because what you're looking at is, once I've taken the absolute value of the terms, that is the series I'm testing. And that series converges by P series. So the only explanation, the only test that I used was P series, but I happened to test the series that is the absolute value of the terms in this one. Now, back over to look at the 3. This one is a P series with a P that is 1/3. That's a diverging P series. So if I can see that if that's an alternating series, then the absolute value, which is this, will decrease to 0. As an alternating series, it converges, but without it, it is a diverging P series. I must do 2 tests because I am testing 2 different infinite series. I am testing this infinite series, and I am additionally testing the infinite series of 1 over cube root of n. For this one, I'll put down it is converge by P, or what am I saying? I already said it was diverge. Ha ha ha. Diverge because the P is 1/3, which is less than 1. And I do want to make sure you're clear that this was produced by taking the absolute value of the original formula. That's a cube root of n. Okay, so I took the absolute value of the formula, I tested that series, I got diverge. Now, I'm testing this series as is. This series is an alternating series. The absolute value of just the terms, not the series of the absolute value. This is just part of the alternating series test. It's asking what is the formula if I take all the negatives out. And this is the formula. If it is an alternating series, then all you need are the absolute value of the terms to decrease to 0. I'm going to start by just saying decreases to 0. And that is officially by the test expressed by saying that the n+1th term is smaller than the nth term. And then I say that it's decreasing to 0 by adding in limit as n approaches infinity of the formula is 0. So the absolute value of the terms decrease to 0 with this alternating series. The alternating series converges by alternating series test. However, when I take the absolute value of the terms and I actually create a new infinite series based on those terms, that series diverges. When I take the absolute value here, it's in the middle of a test with the assumption that I'm asking if the series, with all of its positive and negative glory, is able to converge or diverge. But this testing is forcing everyone to be positive and then lining up in their infinitely long line of series and asking, does this converge or diverge? Now that everybody's turned the same exact direction. And that makes it harder to converge. So situations where they converge, but the absolute value of the terms create a series that diverges, that is conditional convergence. So that is converge conditionally. And what tests were used? We had to use the alternating series test and the P series test. Those were the two tests used to determine conditional convergence. Then we have one more out of the 3. And the first thing I told you to do was take a look at whether the terms are heading to 0 or not. Is this heading to 0 as n approaches infinity? If you know how slow a logarithm goes, you know the answer is, yeah, no, this is heading to infinitely large because the ratio of numerator to denominator is that square root function is going to grow at a rate that causes its distance to the natural log to become infinitely large. Now, if you don't believe me, L'Hopital. If I L'Hopital, then I take the derivative of the square root of n, and then separately I take the derivative of the natural log of n, and it's time to play a rearrange game. This 1/2 in the numerator is going to create, in a singleton fraction, a 2 in the denominator. In the numerator, I have a negative exponent. That's going to move to the denominator if I'm looking at just the one big giant denominator. And it's going to have a positive 1/2 exponent when I move it. Let me emphasize this fractional line is this fractional line. And then lastly, we have 1 over n in the denominator can reciprocate to the numerator as n. So this is what it turns into when I simplify. Then I simplify a little bit further, and I end up with the square root of n divided by 2. Now take a look at that limit and think. N is approaching infinity. That is so infinity. So what you're seeing here is I may have an alternating series, but each term is larger than the previous term. That's going to cause me to head back and forth, further and further and further and further. And I'm going to oscillate between a positive and a negative infinity while running forward and backward. So what I don't want to do is waste my time on alternating series test. It will be an excessive test that doesn't give you any information beyond the answer that we're going to end up with. So you want to realize it's not going to get you anywhere. It won't even be able to pass the alternating series test. Take it to the nth term test for divergence. And with that, you have an oscillation toward infinity. Now, if it was an oscillation toward 0 of positive negative numbers, the answer to this limit would be 0. But because it is not oscillating to 0, this limit is a does not exist due to oscillation between two distinctly different sizes or places on the number line. And in fact, it's going to positive and negative infinity, very, very different places. So with that alone, right there, that shows divergence of the series. And the only test used was the nth term test. That was it. And I do believe that that concludes. And now we have 3 videos of the entire practice test. Good luck studying. I will see you online or in person.